तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we began a discussion on the procedure for device analysis. In this lecture, we will continue this discussion. In the last lecture, we introduced the continuity equation and then summarized the 5 basic equations of device analysis. We saw some methods of approximating these complicated looking equations. Some of the approximations we saw were the equilibrium approximation, in which the current Jn and the current Jp can be assumed to be 0. Then we saw a deviation of this approximation called the quasi-equilibrium, when the equality signs can be replaced by approximately equal signs, and then these currents Jn and Jp can be set equal to 0 approximately. Then we saw the steady state approximation or assumption, according to which this particular time varying term here in the continuity equation for electrons and a similar term for the holes can be set equal to 0. In a deviation of this approximation called the quasi steady state approximation, we can still set these two terms as 0, but the equality sign is replaced by an approximately equal sign here. That means the right hand side of these two continuity equations are approximately equal to 0 in quasi-static approximation. Then we saw the diffusion approximation, in which the currents for any particular type of carrier under a certain situation can be assumed to be solely due to diffusion. So for electrons it would be this term, and for holes it would be this term. Under the diffusion approximation and steady state conditions, and when the semiconductor is uniformly doped, we have seen that the continuity equation simplifies to an equation whose solution is exponential or hyperbolic in nature. In this particular lecture, we will continue with the other approximations which are possible. Let us look at the approximation related to the space charge. So space charge neutrality, what does it mean? So space charge neutrality means that the term rho can be set equal to 0 in the Gauss's law. Rho is the space charge. So if it is a one-dimensional situation, then it means dE by dx is equal to 0, which in turn means that the electric field is constant with x. In a one-dimensional situation. So in any region of the semiconductor, if the space charge is 0, it means that the electric field is constant with x, if it is a one-dimensional situation. Now a deviation of this charge neutrality condition, which holds in many situations, is the quasi-neutrality condition. As per which, even if rho is not exactly equal to 0, it can be assumed to be approximately equal to 0. Now, what is the implication of this quasi-neutrality or charge neutrality conditions? How does it help us to simplify the analysis? Now, according to this quasi-neutrality condition, for example, the excess carrier concentration of holes and electrons are approximately equal. So if the semiconductor under equilibrium conditions is obeying space charge neutrality, and now if you are creating excess carriers in the semiconductor, then even if your excess carriers delta p and delta n are not exactly equal but they are approximately equal, which means if quasi neutrality holds, then delta p is approximately equal to delta n, and in such a situation the simplification is that you only need to solve either for delta p or for delta n and not for both. So noting the fact that the Gauss's law is also simplified under the neutrality or quasi neutrality condition, that is, we don't have to solve this equation at all, the Gauss's law equation at all. We have removed the Gauss's law equation, that is one equation out of the 5, and further, since delta p is equal to delta n approximately, we can either solve for holes or electrons, which means we need not solve for hole continuity equation and hole transport equation and electron continuity equation and electron transport equation. Instead, we could solve any one pair of equations. So the quasi neutrality condition reduces the complexity of the problem, since we only need to solve for only 2 equations out of the 5, any pair of equations either for holes or for electrons. By pair I mean the transport equation and the continuity equation. Now let us understand this delta p approximately equal to delta n clearly. In keeping with the explanation that we have given for quasi equilibrium and quasi steady state or quasi static approximations, delta p approximately equal to delta n means that the individual terms delta p and delta n, the values of this are much greater than the difference between these. So delta p and delta n are individually very large and the difference between them is very, very small as compared to this. This is very important to remember, because we may find that delta p minus delta n may be a significant quantity in absolute terms, but still you can say quasi neutrality holds if this difference is much less than the individual magnitudes of delta p and delta n. We will be illustrating some of these ideas with the help of examples, okay, a little later. Now let us look at another approximation related to the space charge, and this is the depletion approximation. The depletion approximation means that it can happen that in a given region of the semiconductor the free carrier concentration is very, very small. So in terms of the equation, this would mean when we write rho is equal to q times Nd plus p minus Na minus n. This means that you can have a situation where this is approximately equal to q times Nd plus minus Na minus. So this is the meaning that the free carrier concentrations p and n are negligible. So again let us understand this meaning of p and n being negligible. Actually you can see from this equation it is not strictly the p and n in individually that need to be very, very small, because what matters is p minus n. If this p minus n is much less than this quantity Nd plus minus Na minus, you can say the depletion approximation hold. So that is p minus n is in magnitude is much less than Nd plus minus Na minus. So this is the meaning of depletion approximation. Now the depletion approximation is often used to describe space charge layers which occur near junctions such as p-n junctions, the MOS junction and so on. We will see this when we take up these devices later on. As a corollary to the depletion approximation, we will introduce the concept of what is called the Debye length. The Gauss's law can be written in the case of depletion approximation as follows. Let us take an n-type semiconductor. Further, let us assume that there is only one type of doping, that is donor doping. There is no acceptor doping. If that is the case, then the depletion approximation under depletion approximation, the space charge can be written as q times nd plus. So this is the expression for the space charge under the depletion approximation. We have removed the p and n terms because the region is depleted of free carriers and there is no Na minus. So Gauss's law becomes dE by dx. I am assuming a one dimensional situation is equal to q times nd plus by epsilon. We can write the dE by dx in terms of the potential. In other words, we can write the Gauss's law as the Poisson's equation. So when we do that, you put E equal to minus d psi by dx, you will get d square psi by dx square is minus q nd plus upon epsilon. We can transform this equation by multiplying and dividing by the thermal voltage. Now let us look at this term in brackets. The dimension of this term is 1 by length square because dimension of Vt is potential and left hand side you have potential by length square. So this term q nd plus by epsilon Vt is 1 by length square. So we write it here q nd plus by epsilon Vt is equal to 1 by length square, and this characteristic length is the Debye length, Ld square. Okay. So this equation can be rewritten in terms of the Debye length as d square psi by dx square equal to minus Vt upon Ld square. So the Debye length in this particular semiconductor, we are assuming a uniformly doped n-type semiconductor, is given by, take from here epsilon Vt square root of this term epsilon Vt by q times nd plus square root. This is the Debye length. So you see that it depends on the doping level. Now what does the Debye length indicate? What is the physical significance of the Debye length? It is very clear from here that the Debye length tells you how the potential varies with distance, okay, in a depletion region, in a space charge region near the wherever the space charge region is there, how the potential varies with distance. Okay, so this is a characteristic length that describes this variation. So like the diffusion length which we introduced in the previous class describes how the excess carrier concentration decays with distance when the carriers are diffusing and recombining. The Debye length describes how the potential varies with distance in the depletion layer. Now we will discuss two other approximations related to the Gauss law or Poisson's equations which are employed. One is called the Chargesheet approximation. And the other one is called the Gradual channel approximation. The charge sheet approximation is basically used to describe the charges due to free carriers near the interface or surface. So when free carriers are accumulated near the surface for any reason, so supposing you have a semiconductor in which somehow there is an electric field on the surface and the free carriers are accumulating. So let us say this is an n-type semiconductor. Now electrons will be attracted here to the surface. So since they are mobile carriers, they will try to stick very close to the surface. So in such a case, we can assume that the charge due to mobile carriers is entirely near the surface, or it is a charge sheet. So this is what is meant by charge sheet approximation. Although in practice the charge will be high here and then gradually the charge will reduce, but the thickness over which this change occurs is so small that you can assume the charge region to be a charge sheet. More about this we will discuss when we take up the MOS capacitor. This other approximation called the gradual channel approximation is used to convert a two-dimensional situation into a one-dimensional situation approximately. So why exactly this approximation is called gradual channel will become clear when we take up the MOSFETs where this approximation is used, but here we will mention what this approximation essentially involves. If the situation is two-dimensional, the Gauss law can be written as dou Ex by dou x plus dou Ey by dou y is equal to rho by epsilon. In a two-dimensional situation, you have Ex as well as Ey. Now, it can happen that one of these terms can be very small compared to the other term. So for example, dou Ex by dou x may be much less than dou Ey by dou y, in which case we can neglect this term and your Gauss law then can be written as, so if then dou Ey by dou y is approximately equal to rho by epsilon. So although the situation is two-dimensional, because the variation of the x component of the electric field with x is slower than the variation of the y component of the electric field with y, okay, we can neglect this term. So please understand here that we are not talking of the absolute values of the x component and y component, but rather the variation of the x component in the x direction is being compared with the variation of the y component in the y direction. So conversion of this two-dimensional situation into one-dimensional situation, okay. This simplifies the analysis. So we will discuss more about this approximation when we take up MOSFETs where this approximation is used. Now the various approximations that we have employed, one must understand about one thing about them, and that is that throughout the device volume a single set of approximations may not be valid. So how do you analyze a device using these approximations in practice? This is a very important thing that we must understand. So let us look at this slide which summarizes the procedure for device analysis. As is written here, the same set of approximations may not hold over the entire device volume. Hence, partition the device into different regions. This is the first important step in analysis. So you know, as the word analysis implies, analysis means separation of the whole into parts, understanding the parts in isolation, then combining the understanding so obtained to understand the whole. So please understand that analysis always involves some separation of the whole into parts or separation of the device into various regions. So supposing this is our device, then this device will be separated into various regions. So for example, if we take a p-n junction, so you have p and n regions here. This is our device. For the purpose of analysis, this will be separated further into regions like this. For example, we will isolate this region. This is called the space charge region. Here I am not discussing the p-n junction analysis in detail. Please understand, I am only trying to show what is meant by partitioning a device, and how you decide how to partition a device, that is a separate topic that we must address when we consider the particular device. Okay? Now we are only illustrating what is meant by partitioning of the device into various regions. So p-n junction, for example, is partitioned like this. Near the junction you have a region that is the space charge region. And these two regions are the neutral regions. So neutral or quasi-neutral if it is non-equilibrium. Okay, so this is one way of partitioning this device, partitioning of a p-n junction for analysis. Now the boundary between the quasi-neutral or neutral regions and the space charge region is not abrupt in practice, but we have to identify some boundary. Okay, this is one of the approximations that one has to do. Okay, so this is the first step in device analysis. Now let us look at the next step as shown in the slide. Analyze each region using a suitable set of approximations and boundary conditions to obtain the electron concentration n, the hole concentration p, the current distribution Jn, current density for electrons, the current density for holes, and the electric field. Obviously all these are obtained as a function of the distance in that region. Now approximations for different regions can be different. This is the very important thing one must note. So for example, in this case of the p-n junction, you may use one set of approximations in the space charge region and a different set of approximations for the p and n regions, neutral regions. That is what is meant here. So using different sets of approximations, you analyze each of these three regions to obtain n, p, jn, jp and e in those regions. This is the second step. Now let us look at the final step. The final step is combine the information regarding n, p, jn, jp and e obtained in the different regions, ensuring continuity of these parameters across the boundaries, separating the regions to obtain the complete picture. Okay? So these are the three important steps in device analysis. So the first step is partitioning the device into different regions. The next step is analysis of each region using suitable set of approximations and boundary conditions to obtain n, p, jn, jp and e in that region. Different approximations may be employed in different regions. And final step is combining the information regarding n, p, jn, jp and e obtained in the different regions so as to obtain the complete picture. This, when you are combining the information, you must ensure that the parameters n, p, jn, jp and e are continuous across the boundaries. Now we will take an example, a simple example to illustrate some of the steps in the analysis of devices that we have discussed and how the approximations can be applied. Okay? So this example is as follows. So you have a semiconductor which is terminated on a ohmic contact at one end, and the other surface, the opposite surface, is illuminated with light. The thickness of the semiconductor is 200 microns. Let us look at other details of the semiconductor and what is expected to be done. The semiconductor is p-type with doping level of 10 power 17 per centimeter cube. The lifetime of minority carriers, that is electrons, is 1 microsecond. Now the light energy is greater than energy gap of the semiconductor. Let us assume that the semiconductor is silicon in this case, and intensity is 10 power 16 photons per centimeter square per second. So this is incident on a non-reflecting surface of 1 centimeter square area. So what it means is the area of this surface which is illuminated is 1 centimeter by 1 centimeter. So this is 1 centimeter and that is also 1 centimeter, and the surface is non-reflecting, so the entire light is absorbed, nothing is reflected. This is not a good assumption at all, but we are making a simplifying assumption so that the problem becomes simple. Now the thing to be done is obtain N, P, Jn, Jp and E versus X within the semiconductor under steady state conditions and check the validity of the approximations employed. Now here X direction is along the thickness, okay, of the semiconductor. So let us do this example. The first step in the solution of any problem in solid state devices is a qualitative analysis. This means that we must sketch the distributions of various parameters as a function of distance based on simple logical reasoning without writing any equations, using a knowledge of the physical situation. So the situation is depicted on the diagram. This is a sample and light is falling on it on one surface. The intensity of light is IPH. This is a symbol we use to indicate the intensity of light, that is number of photons per centimeter square per second. Then you have an ohmic contact on the left hand side, that is the contact between metal and the semiconductor. The situation in the sample is depicted in this flow diagram. On this face here you have electrons and holes being generated. This is surface generation, that is the unit of generation is per centimeter square per second. So per unit area of the surface, where area of the surface is in that direction. So that is the area we are talking about. Now the carriers which are generated at the surface all move inside because of diffusion, because at the surface the concentration of carriers is high, whereas within the bulk it is low, so there is a concentration gradient. Now what is shown here is that all the carriers which are generated are moving inside. So these are electrons and these are holes. This is equivalent to saying that this surface has surface recombination velocity equal to 0, because none of the carriers which are generated at this surface are recombining there. This may not be true in practice, but we are making this assumption to simplify the problem. Now carriers which are moving inside, what happens is during their motion they also recombine. This is what is shown here. Finally some carriers are still left by the time you come to this particular surface, the contact where the ohmic contact is there. So all the carriers which are remaining until this point will recombine at this contact. Now let us sketch the concentration of holes and electrons based on this picture. We shall make the low level assumption, which means that the excess minority carrier concentration is much less than the majority carrier concentration, and therefore when we sketch the majority carrier concentration, that is hole concentration and minority carrier concentration on a log scale, note that we must use a log scale because otherwise we cannot show both concentrations. When we do this, the majority carrier concentration will appear to be almost undisturbed. So this is why it has been shown by a constant line. This is because of the low level assumption. Now minority carrier concentration of electrons, however, is disturbed at this end by a value equal to delta n, because there is a surface generation there, and this is shown also in the flow diagram. So from this value delta n, the excess electron concentration decreases progressively, and when it comes to this edge where there is an ohmic contact, please note here there is an ohmic contact. When it comes to this edge, the excess carrier concentration becomes 0. This is the consequence of statement of the ohmic contact. Let us try to see why ohmic contact implies 0 excess carrier concentration. Now ohmic contact can be interpreted in terms of the surface recombination velocity. Surface recombination velocity tending to infinity. That is the meaning of ohmic contact. We will not discuss this point in detail, why at an ohmic contact surface recombination velocity is infinite. This has to do something with the structure of the interface between metal and semiconductor. That is beyond the scope of this particular course. So you just accept it that ohmic contact means infinite surface recombination velocity. Now let us see how infinite surface recombination velocity is equivalent to 0 excess carrier concentration. Now recombination rate at the surface here is given by surface recombination velocity multiplied by the excess carrier concentration at that point, that is here. Delta n is excess electron concentration. Okay, so what we are sketching here is delta n. So delta n is actually this difference. This is the equilibrium concentration, this is the concentration under illumination. Okay, so the difference between these two is delta n. So delta n 0, so value of delta n at this point. This is the equation for surface recombination. Now surface recombination rate has to be finite, no matter what is your S, that is the surface recombination velocity. So we can write delta n 0 in terms of Rs and S as delta n 0 is equal to the surface recombination rate minus S. Since Rs is finite, it has to be finite, but S is tending to infinity because it is an ohmic contact. This means that the excess carrier concentration tends to 0. So delta n tends to 0 as S tends to infinity. Okay. So this is the reason why excess carrier concentration is 0 at an ohmic contact. So this is the distribution of minority carriers as a function of distance. I emphasize that delta n is equal to delta p, so you also have excess holes, but on a log scale under low injection level, as we have discussed earlier, there will not be any disturbance seen. Okay, so you are not able to see that delta p here. So it almost appears to be constant, equal to the equilibrium value on a log scale. So here this is on a log scale. Now let us move to a representation of the excess carrier concentration alone, because that is of interest to us. We are not interested in both majority carrier concentration and minority carrier concentration. For our analysis, we need the excess carrier concentration. So this is shown here in a linear scale. So delta is the excess carrier concentration as a function of x. We are not putting a suffix p or n because delta p is approximately equal to delta n. This is the assumption of quasi-neutrality. So we are making the assumption of quasi-neutrality. We will prove at the end that these assumptions, namely low level and quasi-neutrality and the other assumptions, are valid. Okay, now continuing. So what we sketch here is the distribution on a linear scale. Delta n is excess carrier concentration at the right hand surface, illuminated surface, and excess carrier concentration at this boundary is 0, and there is a gradual change from delta n to 0. Okay, we are expressing everything in terms of the excess minority carrier concentration. Okay, now let us move to the current distributions. If you make the diffusion approximation for minority carriers, that is Jn, the electron current in a p-type semiconductor is approximately equal to the current because of diffusion. Okay, that is the assumption we are making. So this is the diffusion approximation. Please note that this holds only for minority carriers. Okay, we will prove at the end that this holds, but now we will make the assumption. So if you make this assumption, then the electron current can be obtained from the slope of this distribution, because diffusion current is the diffusion coefficient multiplied by the slope of the excess carrier concentration. So this is Jn. Note that Jn is not 0 here. This is because the distribution of the excess carrier concentration is such that the slope here is not 0. We have discussed this earlier, that the slope of the excess carrier distribution is 0 only when the sample is infinitely long or very long compared to the diffusion length. Okay. Now, what about Jp? How do you get Jp? Now you note that this device is open circuited. So J, which is Jn plus Jp, is 0 because the device is open circuited. What is the meaning of open circuited? If you come back here, there is no wire connecting this end to the other end. Okay? So if there was a wire connecting the illuminated surface to the ohmic contact, then we could say that the device is short circuited. Okay? Now there is no such connection, so device is open circuited. So when device is open circuited, Jn plus Jp, that is the current entering the terminal, is 0. And since if the current entering the terminal is 0, since it is a steady state condition, we have shown earlier that the current is uniform throughout the device under steady state. Okay? You should see the consequence of steady state that we have discussed earlier. So dj by dx is 0. So the current inside the device, the total current, we are not talking of individual currents, the total current in the device due to electrons and holes is constant. So whatever is the value at the terminal, same is the value inside the bulk, so it is equal to 0. So since this is true, you get Jp is minus of Jn, simply minus of Jn. So this is what is plotted here. J is shown to be 0 throughout and Jp is negative of Jn. So this is a curve that is similar to this but reflected onto this particular surface. Okay? So this is a reflection of this. Now let us come to the electric field. Why is an electric field present in the device at all? The electric field can be traced to this particular condition, that J, that is Jn plus Jp, is 0. How? Now notice that if the currents were entirely because of diffusion for both electron as well as hole, then the hole current would not be equal to the electron current, because the hole diffusion coefficient is less than electron diffusion coefficient. So since dp is less than dn, Jp diffusion in magnitude is not equal to Jn diffusion. Okay? But as shown here, J has to be 0. So Jp has to be equal in magnitude to Jn, although negative in sign. So how can you make these two currents equal? An electric field is set up in the device which is in this direction, from illuminated surface to ohmic contact. Okay? Now what is the role of this electric field? Notice that if the electric field is in this direction, it will aid the movement of holes from right to left. Okay? But it will oppose the movement of electrons from left to from right to left. Right? The same electric field will oppose the movement of electrons from right to left, but it will aid the movement of holes. Now we have shown here the electrons are also moving from right to left, holes are also moving from right to left. So this movement will be aided by this electric field, but this movement will be opposed by this electric field. So in this manner, the diffusion current of holes, okay, is aided by the electric field which is in this direction, and the movement of electrons is slightly opposed. So this is how the diffusion current of electrons is slightly reduced and the whole current of electrons is increased. In fact, the effect of electric field on electrons is small because the electron concentration is small, but the effect of electric field on whole current is large. So in effect what we can say is the electron current is almost equal to diffusion current. We will show this at the end. We have already made the diffusion approximation, but the whole current is because of both drift and diffusion, and the drift of whole current is such that it adds to the diffusion so as to make this current equal in magnitude to Jn, because that is a condition we should maintain device is open circuited. So that is the role of the electric field. It is to bring the whole current in step with the electron current, so as to maintain a total current J of 0 value. So the electric current is the electric field is in the negative x direction, that is why it is shown on the negative axis. Further, whenever the currents are large, electron and hole currents are large, to bring hole and electron currents in step, you will need a larger electric field. That is why electric field is larger here and it decreases progressively. Note that here electric field is not 0 because the currents are not yet 0. Okay? So you need some electric field to keep these two currents in step. So that explains this distribution of electric field. Now we can readily derive the space charge distribution from the electric field distribution using Gauss's law. So Gauss's law says that rho by epsilon is equal to dE by dx. So rho is equal to, this rho is equal to dE by dx into epsilon. That is what is shown here. You take the slope of this, you get this. Okay? So rho is negative because you see the slope is negative. The fact that rho is negative is seen from here, and then you can see that the space charge here is 0. This is because the excess carrier concentration is 0 at this point. So if excess hole and electron concentrations are 0 as shown here, obviously the space charge should be 0. Now there are two impulses here. This impulse is because there is a step in the electric field like this. So this is the positive charge sheet from where field lines emanate and they terminate throughout the bulk, and then that is why the field decreases, but some lines still remain when you come to this end and they terminate on a negative charge sheet that is shown here. So that is from the Gauss's law, it is this step that is responsible for this particular impulse. So the area under this curve plus this will totally show the negative charge, and this shows a positive charge. These two charges will be equal. So this is how, based on qualitative analysis, okay, we can draw the distributions of N and P, Jn and Jp and E. Okay. Now the next step is to do a quantitative analysis so that we get the values of various critical parameters such as the boundary values of the electric field, the current and the excess carrier concentration, and we also need an expression for these curves, okay, shown here. So this we will do next. Now the excess carrier distribution obtained from the diffusion equation, that is the starting point of quantitative analysis. We use the hyperbolic form of the solution of the diffusion equation because the sample is finite. We have explained why for a finite sample a hyperbolic form of equation is more suitable, and it will also become clear in this analysis how the hyperbolic form is more suitable. Now value of delta n at 0, x is equal to 0 is 0 as shown here. So if you substitute this condition here, you will get the result that C should be equal to 0. This is because when you put x is equal to 0, this term will vanish, left hand side is 0, but this term will be unity, cosine hyperbolic of 0 is unity, so C will remain, so you will get C equal to 0. Using a similar approach, you can write delta n at W is equal to capital delta N, that is this delta n at W, and then since now you are left only with the sine hyperbolic term, you will get from this condition the value of D to be delta n by sine hyperbolic W by ln. So we can write the solution as delta n x, excess carrier distribution of electrons, is delta n into sine hyperbolic x by ln divided by sine hyperbolic W by ln. Now we still do not know what is the value of delta n. To know this, we should proceed to the current distributions. Let us see how the current distribution will give us the value of delta n. Now the Jnx, that is electron current by diffusion approximation, is given by q dn, the gradient of excess electron concentration. So substituting for delta n from here, we can get this equation Jnx equal to q dn delta n upon ln into cosine hyperbolic x by ln by sine hyperbolic w by ln. So Jnx is of the form of cosine hyperbolic x by ln. This is clear from here. You see the shape, it is non-zero at this point and then it goes on increasing. So this is the shape of the cosine hyperbolic function. Now the boundary value of Jn at x is equal to w, Jn at w, that is Jn here. This is q times I ph, that is intensity of illumination. So this is q times I ph. This is given in the problem. How? Let us look at this particular situation. The intensity of photons is IPH and each photon is giving rise to an electron hole pair. So this is how the current results or current density results. So Q times the photon intensity is simply the magnitude of the current density of electrons at that end. So that is how you get this. Now you equate, you substitute x is equal to w in this equation and then equate the result with this and then you solve for delta n, and the result will be delta n is equal to ln into I ph, intensity of photons, by dn into tan hyperbolic w by ln. Now we can evaluate delta n by substituting the various values. Dn, this is 17 centimeters square per second. How do we get this? Dn is equal to mu n into Vt. For 10 power 17 per centimeter cube doping given in the problem, this mu n turns out to be 668 centimeter square per volt second from the mobility versus doping formula. Vt is the thermal voltage. So you multiply Vt and 668, you will get 17 centimeter square per second. Now how do we get ln? We write ln is equal to square root of dn tau n, which is equal to square root of dn is 17 centimeter square per second, tau n is 10 power minus 6 seconds, 1 microsecond. So the result is square root of 17 in 10 power minus 6 centimeters, and this turns out to be 41 microns. So this ln is 41 micrometer. IPH is 10 power 16 per centimeter square per second. Now W by ln, W upon ln is equal to 200 microns by 41 microns. So this is about 4.88. So this W by ln is 4.88. So you substitute all these values and you will get the result. Delta n is equal to 2.4 into 10 power 12 per centimeter cube. Okay, so this is 2.4 to 10 power 12 per centimeter cube. Now substituting this delta n in this equation, we can also get the equation for Jnx. In quantitative terms. So it turns out after substituting the various values you will get the result 24 cosine hyperbolic x by ln microamps per centimeter square. Okay, so which means this is 24 microamp per centimeter square, and this value is 1.6 milliamps per centimeter square. Now let us go to the electric field distribution. Electric field distribution is obtained from the condition Jn plus Jp equal to 0. So we write the various terms for Jn and Jp. So Jn drift, Jn diffusion, Jp drift, Jp diffusion. Now in this whole equation you note that dn by dx and dp by dx both can be approximated to be d delta n by dx because of quasi-neutrality assumption. Further, because of the low level assumption, this P, which is the majority carrier concentration, is approximately equal to P naught, the equilibrium concentration of holes, and the N is much less than P, because N is minority carrier concentration. So in fact we can neglect this term. Now we can simplify this whole equation, and noting that left hand side is 0, you will get the equation Ex is equal to dN by dP minus 1 in brackets into Vt by P naught into d delta N by dx. See that dimensionally this equation is electric field. Vt is volts and P naught and delta N have the same dimension, so they cancel, and x is dx is centimeters, so volts per centimeter. Okay, so this is electric field. Now you can substitute for delta N, which we have obtained earlier, and you will get this particular equation, dN by dP minus 1 into Vt by P naught into delta N by Ln into cosine hyperbolic x by Ln divided by sine hyperbolic W by Ln. Okay, so substituting the various values, it turns out this is equal to minus 4 cosine hyperbolic x by Ln microvolt per centimeter. So this is minus 4 microvolt per centimeter, and this is minus 270 microvolt per centimeter, okay, after evaluation. Now finally we need to check the approximations that we have made, namely the low level, the quasi neutrality, and the diffusion approximation for minority carriers. So checking of assumptions or approximations. The low level approximation, if the low level approximation is valid, then delta N by P naught, excess electron concentration or excess minority carrier concentration by equilibrium majority carrier concentration, should be much less than 1. Now this is less than or equal to the maximum value of delta N divided by P naught. So maximum value of delta N is this. Okay. Now you substitute for delta N and P naught, which we have solved for, and you will get the result 2.4 in 10 power minus 5, which is very clearly much less than 1. So the assumption of low level injection is therefore valid, very much valid in fact. Next, let us go to the quasi neutrality assumption. Quasi neutrality means delta N approximately equal to delta P. This is what we must prove, which is equivalent to saying delta N minus delta P, that is the difference of the two, should be much less than delta N or delta P, that is the individual components, which is the same as saying that delta N minus delta P, the modulus of this divided by delta N, should be much less than 1. Notice that we are taking modulus because we do not, because delta N minus delta P can be either positive or negative. We are only interested in the magnitude. Now delta N minus delta P is nothing but the space charge divided by the Q. So showing this is equivalent to showing rho by Q by delta N much less than 1. Now rho by Q by delta N, the modulus of rho by Q is taken in the numerator, can be written in using the Gauss's law as epsilon by Q dE by dx by delta N. So rho by Q is epsilon by Q into dE by dx. Now we have solved for E as a function of x, and we have solved for delta N as a function of x. These are the results that we have obtained. Okay, delta N is this and Ex is this particular result. So you can see from here that when you differentiate E with respect to x, the cosine hyperbolic function will become sine hyperbolic function, and therefore when you take the ratio of delta N to differential of electric field or dE by dx, the term that is dependent on x will cancel out. Okay, and that is what is happening here. You finally get a interesting and constant result like this: epsilon Vt by Q ln square into dN by dP minus 1 into 1 by P naught. Now if you evaluate this, you will get it as 1.7 in 10 power minus 7, which is much less than 1 again. Now here one point I must emphasize, the value of dn by dp which we have used earlier also, it was not clarified how we obtained. So just as we obtained dn for 10 power 17 per centimeter cube, we obtained dp also in the same manner, okay, and then if you take dn by dp, you will find that dn by dp will be 2.85. So that is the value that has been used here. Now finally let us discuss the diffusion approximation for minority carriers. So to prove the diffusion approximation, we must take the ratio of the drift current of electrons to the diffusion current of electrons, and we must show that this ratio is much less than 1. So therefore diffusion dominates over drift. Now this ratio can be written as Qn mu n into E divided by Q dn d delta n by dx. Okay, this is drift, this is diffusion. Again we are taking modulus because the currents can be in opposite directions, okay, and we don't want to use a negative sign for any reason. It is not useful for us. We are interested in the magnitude. Now we should therefore find out E divided by d delta n by dx. Okay, this q will cancel. So E divided by d delta n by dx. Now Ex we have shown to be given by this particular formula. So E divided by d delta n by dx is very simple equation, which is this. This is what is shown here. Okay, where now here n we must recognize is approximately equal to delta n itself. This because for minority carriers the excess carrier concentration will normally dominate over the equilibrium concentration. So we can simply replace n by delta n approximately over most of the device, and therefore your result will turn out to be of this form: delta n by p naught into dn by dp minus 1. Interestingly, delta n by p naught is the injection level. So if the injection level is low, definitely this ratio is going to be much less than 1. So you get this ratio 4.4 in 10 power minus 5, which is much less than 1. So diffusion approximation is justified. In fact, this particular expression also shows how the diffusion approximation is linked to the low level approximation. If low level is valid, the diffusion approximation is also valid. Now we will summarize the discussion of the last 2 lectures. So we have covered the following topics. First we considered the continuity equation for device analysis. Then we summarized the 5 basic equations for device analysis, namely the transport equations for electrons and holes, the continuity equation for electrons and holes, and the Gauss's law. Then we discussed the standard simplifications of the equations. We have explained what is the meaning of the word analysis, that is separation of the whole device into parts, understanding the various parts of the device in isolation, and then combining the understanding so as to understand the whole of the device. So here we have explained that the analysis involves the solution of the 5 basic equations simultaneously to give the parameters, namely n, p, jn, jp and e as a function of distance. Then we illustrated the analysis using a solved example. Now before we take up the next chapters, which involve analysis of semiconductor devices such as p-n junction, bipolar junction transistors, MOSFETs and so on, it will be useful for us to summarize some of the characteristic material parameters that we have come across in the last 18 lectures. Now these parameters are the energy gap, direct or indirect. The symbol for this energy gap is also shown there. In fact, the symbol for all the important parameters have been shown. Then the doping. For doping there are 2 parameters, the concentration and the impurity level. Then the mobility of electrons and holes. Then the lifetime and mean free time of carriers. Then the diffusion length, Debye length and mean free path or mean free length. There are the 3 characteristic lengths. Surface recombination velocity, and finally the dielectric constant. So whenever we derive equations for terminal characteristics in terms of the physical parameters, these characteristic parameters will come into the picture.